Okay, so we finished the introduction last time, and we'll begin with the perturbations today. So, this is a part 2 in the cosmology of the very early universe. This is cosmological perturbations. And here for the tensor modes, we will make contact with what we saw for gravitational waves in asymptotically flat case. Okay, so what we saw last time, where we ended was really that we're motivated by the inflationary scenario, so we assume that the only matter field is a scalar field phi with a potential V of phi. We are in the homogeneous isotropic case, therefore this phi will only depend on time. And then we found that our basic equations were the Friedmann equation for the background geometry. This is equal to 8 pi g over 3 times rho. The Raychaudhuri equation, which is A double dot over A is equal to minus 4 pi g over 3 times rho plus 3p. And finally, the equation for the scalar field, which we write down again in terms of the using homogeneity and isotropy. So it's a function, it only depends on the time variable, so phi double dot plus 3h times phi dot. This is h is just a dot over a dv by d phi. And one of the homework exercises would be to check that these equations are consistent. In particular, these two imply this, and you can also see if in fact if it is true that any two of them imply the third one. Okay. And now what we want to do is to do perturbations about it. So this is the background geometry. So this down here. Background geometry is then the metric GAB. It's just given by minus dt squared, or minus dt squared plus a squared of 3 times dx squared. And then we put a bar here just to avoid the notational issues, because most of the time we are going to use conformal time. So therefore, and this is the same as a squared of eta. A bar of t is not the same function of t as a is a function of eta, and that's why we have a distinction here. In cosmology literature, one calls a of t, eta and a of t, they're the same symbol. Mathematically, it's a bit confusing. So minus eta dx squared, where a satisfies these equations up here, and we've got a background field phi. The phi satisfies this equation up here. So this is our background, and we want to perturb around this background. So this is homogeneous and isotropic. And perturbations are general. Notice that the scalar field, because it's homogeneous and isotropic, the scalar field does not die at infinity, and therefore the stress-free tensor or the density is really spatially constant. It does not decay at infinity. So of course this is not asymptotically flat in any sense that we discussed before. So that is why we need a new kind of framework to describe, for example, the gravitational waves in this context. So perturbations are general, so there are no symmetries in general. That is to say, there are no symmetries. They are functions of x and t. And then what we want to understand is what these perturbations are. So we can take, as we did in the case of the asymptotically flat context, we can look at either one parameter family of solutions, GAB of lambda and phi of lambda, to Einstein scalar field equation, and or we can put it into action if you like. Well, and then we can just do linearization by d lambda of GAB of lambda is at lambda equal to 0 equal to something that we call gamma AB, or we can, and similarly d lambda of phi of lambda is equal to, let's say, at lambda equal to 0 is this phi up here. And this, of course, phi, and similarly this gamma, it depends on both x and eta. These are not homogeneous and isotropic, these are just general perturbation, just general fluctuations. So I got here the background here, which is given to us. So this background corresponds to GAB at lambda equal to 0 and phi at lambda equal to 0. This is the background which satisfies these various equations, and now we're going to do perturbations up here. Or we can just write this as just, people often do that GAB is just given by the background metric up here. So one often writes this as a squared of eta times. So this eta is really this eta is really the conformal time, but this metric up here is also a Minkowski metric. But it's a conformal metric, it's a Minkowski metric not in the proper time, but in the conformal time up here. This distinction is important, please don't confuse. This really is in this conformal time. And so this Minkowski metric, we can write down the background metric as a squared times this Minkowski metric. So since we use the symbol eta already for conformal time, let me not call the Minkowski metric eta AB, let me just call it G naught AB. This is just the Minkowski metric. And then plus, so let me call this gamma tilde IB. So often people just say that they write down the metric GAB as this plus epsilon and gamma AB. So gamma tilde AB would be a square of eta times gamma AB. So they pull out this factor just to simplify the equations. This was a trick that was found by Lipschitz in the late 40s, very long, 1940s, long time ago. So people write down the linearized metric gamma AB like that, and then we got the linearized scalar field up here that is given up here, and then we have to find out the equations. So of course there are several ways of doing it. We can just take this metric. So let's call it the effect on phi. Let me call it bold-faced phi is going to be equal to the background phi plus epsilon times little phi up here. Again, this is homogeneous isotropic. This is in fact flat, and this gamma AB, however, depends on both x and eta, and this little phi also depends on both x and eta. And then you can put this in the action. You can do the variation of action and keep terms which are only linear in epsilon. That will give you the linearized Einstein equation and linearized scalar field equation for these perturbations. So as in the case we saw while we studied gravitational waves, there's a gauge freedom. Namely, I can take this gamma AB or this gamma tilde AB, which is the a squared times gamma AB, gamma tilde AB, and I can make a transformation. Namely, gamma tilde AB I can add to it Lie derivative by the vector field of the background metric. I can do this. So basically, I got the background metric GAB, which is given to us. This is the G naught AB times a squared, if you like. There is a background metric up here that is given to us, and this is, let's see, let me call it background. This is the GAB of background. GB, a background metric up here. And I just take the lead derivative of that. And that is just a change really in the background metric, but you can think of it as being absorbed into the infinitesimal change being absorbed into the perturbation, and that is a gauge transformation. And at the same time, of course, we have to take phi goes to phi plus C of the background phi that I got up here. So this is the gauge transformation, and this is where one, in a detailed treatment, one should really be very systematic and show that how one can actually use this gauge in order to simplify. Because we have so little time, we're not going to do that. I'm just going to tell you the final results. And again, there are many monographs, books, and so on in cosmology where all these things are done in some detail. Please.
Are we making the distinction between gamma and gamma tilde?
Yeah. So gamma tilde. So this is really just the linearized method. So the G8. So gamma tilde is just a squared times gamma. So gamma tilde is a perturbation of the physical metric, and this is kind of mathematical simplification due to Lifshitz. So therefore, actually, when we do the gauge transformations, this is the fundamental gauge transformation, and then what we're to do is to see what it means in terms of this gamma. Okay. It is not very different from what one does in the Minkowski space-time, where we did linearized gravitational field. Remember that we had the physical metric. I think we call it gamma AB, the physical linearized metric, and we also define gamma bar AB, which are the trace reward, gamma AB minus gamma times theta AB. And then all the equations were written in terms of this gamma bar because they were simpler. But of course, the gauge transformation refers to here. So we find what happens here, and then we just see the effect of the gauge transformation here. The same thing is true here. The gauge transformations we look at with respect to the physical perturbation, and then we can transfer, of course, to how little gamma transfer. So we do that, and then the statement is that we can So we can get this gauge freedom, and we can use this gauge freedom to focus on 2 degrees of freedom of these perturbations. And what are the 2 degrees of freedom of this perturbation? Well, you know, in general relativity, in vacuum GR, we only have 2 true degrees of freedom. These were the 2 radiating modes, for example, that we saw in full general relativity. More precisely, in vacuum general relativity, we can go to the phase space, and we get the metric as a configuration variable, and we get the momentum. It's canonical conjugate momentum. We can go to the phase space. In the phase space, you know that there are 4 constraint equations. Those of you know about constraint systems. These constraints are first class. That's a nice property. As a result, the statement is that the degrees of freedom can be obtained by just taking the configuration variable and subtracting the number of constraints. So configuration variable is a metric, is a symmetric spatial metric. So it has 6 degrees of freedom, and we can subtract these 4, and we find that there are 2 degrees of freedom. And now we're going to scalar field as well. So we're going to scalar field, and for the scalar field we can do the same thing. I got here phi pi. In full nonlinear general relativity, we got phi and pi, this board phase thing here, if you like, phi and pi. And again, we just count the degree of freedom, the configuration variable, and we find that there is 1 degree of freedom. So in all, there are only 3 degrees of freedom. In all, there are just these 3 degrees of freedom. So in the inflationary scenario, there are only 3 degrees of freedom. So what one does typically is to encode these degrees of freedom as follows. Encoding of this. So this is where a systematic work would be needed. I'm just telling you the final answer. We've got 3 degrees of freedom in this inflation scenario, and how are they encoded. So what we do is, we take just the spatial part of the metric. So spatial part of gamma AB, this is the we just take the spatial part of gamma AB, and we then expand it out. Okay. Now the point up here is that we have, so this is gamma AB is a part of this perturbation. This perturbation lives on the background space-time, this background space-time up here, and spatially, the 3-dimensional sections are spatially flat. And therefore, we can still do Fourier transforms in space. See, in general curved space-time, we cannot do Fourier transform because it will be coordinate dependent. But here, we got these symmetries. And because we got these symmetries, namely the spatial metric is just flat, therefore we can do meaningfully Fourier transforms in space, not with respect to time, but in space we can do the Fourier transforms without any problem. Okay, so this is an important point. I hope if you have any questions, you can ask me. If the spatial metric was not flat, but if we are, for example, in a closed universe, again, where I got enough symmetries, it's a group manifold, there's enough symmetries, so we can again do Fourier transform. And similarly, if it was a hyperboloid, then we can also do Fourier transform because we have got enough symmetries up here. So spatially, we can do Fourier transforms. They're not, of course, you don't have to do them, but the degrees of freedom become, very explicit in terms of those, if you do the Fourier transform. Spatially, we can perform Fourier transform, and we'll do that. And now, there's another thing that I'm going to do. The classical theory, this is totally not necessary, but when we go to quantum theory, this will become important. This will simplify things for us. Namely, I'm going to assume the torus topology, if you like. Where the radius of the torus can be extremely large, and so it is observation is not forbidden. And the only reason is because what this enables us to do is to use Fourier series instead of Fourier transform. Why is that going to be important? Well, classically, it makes no difference. I could have just done everything this way. But when you go to quantum field theory, then if in fact space is R3, entire R3, then in addition to the problems which are in short distance, which are the ultraviolet issues, which are the physically the more important ones, there are also infrared divergences. And then I would have to spend a lot of time telling you how to handle those infrared divergences, which really do not play any role in the observational thing that people do, at least at the level that we're talking about, they do not play any role. So I'm just short-circuiting this whole discussion about infrared divergences in quantum field theory that we will have to do in a while, next time, by just assuming that the topology is T3, so I can just use a Fourier transform, Fourier series in place of Fourier integrals. So therefore, I can write down this QAB of x and eta. This will be just written as 1 upon volume. So this is the volume with respect to fiducial metric. We just have a flat metric, which is implicitly here on the 3 manifold that I use in the fiduciary. So I'm just using that volume with respect of the fiducial metric, dx squared volume of the torus. So this volume is not changing in time. It's just fixed once and for all. The proper volume is changing in time because the physical metric is a square of eta times dx cubed. So the proper volume will be given by v, will be given by a cube of eta times this v naught. And I'm just not in this Fourier transform, we're just doing it with respect to the fixed fiducial metric. This is often called co-moving coordinate. This Fourier transform refers to the co-moving coordinates. So times now times phi naught dot k, and then I'm just going to get here QAB, the Fourier transform of k times e to the I. I just am doing the Fourier transform in this particular way, just in the x variable. Eta variable, we don't do anything up here. I'm just doing the Fourier transform up here. And now the point is that this k tilde AB that I got here, this also symmetric second rank tensor. On space, right? Now in this case, momentum space up here. Therefore, there are 6 components. And to talk about transverse traceless decomposition in the physical space-time, that corresponds to, in the Fourier space, that corresponds to decomposition in the radial and the angular directions, as we have seen many times. For example, if in fact, for a vector field, if I say dA VA equal to 0, then its Fourier transform V tilde A of K will satisfy KA. K hat A, VA equal to 0 in the radial direction. This will just become K. So therefore, to talk about the true degrees of freedom, it is convenient just to use the polar coordinates in the momentum space. So we can just take this Q tilde AB now, and I can expand this Q tilde AB in a very simple-minded way. I can introduce in the momentum space. This is like the undergraduate calculus, right? I can introduce a radial vector, a unit radial vector, let me call it k hat, and I have to introduce 2 angular vectors. So I could call them m and m bar. Do you prefer that, or I can call them, okay, or I can call them just something else, u and v, which is real vectors. So u plus iv would be like m, and u minus iv would be like m bar. So let us do that. So this is going to be equal to, so we introduce I got the orthonormal triad, k hat, u hat, and v hat. This is orthonormal. In the momentum space, k hat is the radial direction, and these are in the 2 sphere. These are the angular directions in the momentum space. So we can just expand this. And as you can imagine, there are going to be 6 components, right? Very boring. Namely, I'm going to get some component which is k hat, u hat, u hat, v hat, v hat, and then 3 mixed ones, k hat, u hat, v hat, and u hat, v hat. I'm going to get 6 components. But it is convenient to just regroup them. It's a completely trivial algebraic regrouping. That is done in order to read out the behavior of various components under rotations. And this behavior there's a standard notation for that. So people write this as this object is equal to what one calls the first scalar modes. So this is a function of k and eta. So this is a standard notation. The k is written here because it's kind of a discrete variable, and eta is a continuous variable, is written here. It's not necessary, but that's what one often does. Times, I'm going to get Q naught AB. Q naught AB is this metric, the Friedrichs metric that we have fixed, which is just equal to dx squared. Dx squared plus dy squared plus dz squared. So it's just first thing, just the trace of this object. Okay, that's what I have. Then plus, I get here the second scalar mode, which is written as to be equal to k hat A, k hat B minus 1/3. So this is also a scalar mode. It's radial minus a trace up here. And so you can see here immediately that this object is going to be trace free, because if I contract on these 2 indices, I will get 1. If I contract on these 2 indices, Q hat AB. So there's a Q hat AB. If I contract with this with Q naught AB, I'll get 3, so that will cancel. So this is trace free up here. Then plus 2 vector modes, which are written as 2 times Vk is a vector mode times k hat A, u hat A, k hat B. So this is the mixed components. So it's not a very profound statement. The profound statement is basically that if I project one index in the radial direction and one index in the tangential direction, I'm going to get a sort of a vector in the tangential direction, and that is what we're expanding out. Okay, this vector mode is just a vector in the tangential direction that we're expanding out. So There will be a component in the tangential direction in the u, and there will be a component in v. So what is saying that if I just project this in the one index in the radial direction, the second index in the tangential direction, then I'm going to get a vector in the tangential direction, and I'm expanding it as square root of 2 v1 ua plus square root of 2 v2 va. It's not very profound. And then finally, there is a transverse traceless mode. So finally, you will get that whatever is left over, and that whatever is left over is convention is written to be square root of 2 times. I'm going to get two modes up here, so it's going to be equal to 1 upon square root of 2 times the first tensor, the tensor mode k times u hat a, u hat b minus v hat a, v hat b plus square root of 2 times the second tangential mode, second polarization, second tensor mode u hat a. Okay. So basically, I'm given this tensor q hat AB, and I would like to construct a scalar out of it under rotations. Well, the scalar is obtained by either, if I take the metric itself, so the trace of this is a scalar, because under rotations, it will transform like a scalar. There's no. Whereas, I can also plug two radial vectors, and that is also good. I plug Ka, Kb, that will also give me a scalar. And this is just the rearrangement of the terms. One, we have pure trace, and the other, we have got trace-free part. Everything else I have written down up here is trace-free, because if I contract these two indices, I get 0, because V is tangential, K is radial, and U is tangential and K is radial. And similarly here, if I take the trace, since U is unit, this minus this, trace of this will be 0, and U and V are orthogonal, trace of this is 0. So what we have done is we have taken the trace part out, and then what is left, so therefore we get two objects which are scalar modes. Then I obtain two additional objects which are obtained by the mixed component. These are the vector modes. And finally, I get things which are just transverse to the radial direction, to the K direction. Only I got U and V components up here, and I got transverse. So therefore, to begin with, I would get this a two-dimensional sphere. I'm looking at a symmetric second rank tensor field, so it has three components. But I'm looking at the trace-free part, because trace has already been taken care of, and therefore the trace-free part has two components. And these, as most of you know, are the two polarizations of the gravitational field that we gravitational field that we talk about. So in terms of, if I expand it out all in terms of m's, it will be mm and m bar m bar. So you can just rewrite these things as mm plus m bar m bar. There is no m bar term, because that is pure trace. So this is our decomposition, and this decomposition, we have got two scalar modes, two vector modes, and two transverse traceless tensor modes. The vector modes are also transverse, in the sense that this V hat, U hat times K, U hat times V is for the vector. I hope it is not confusing. Here V is for the vector. That's why I wrote as V up here. Maybe I should use some other bold-faced V. These are just the coefficients, and here you got U and V are the two vectors that I got. Maybe I should have called it W, but now shall I change it and call it W? Is it confusing, or is it okay? Okay, it's okay. All right. So we got here. So here V hat is a vector, and this is just a function, the component of Q in the V hat and K direction, and in the U hat and K direction. So the 6 components of the metric have these two scalars, two
two tensors, two vectors and two tensors, traceless tensor mode. Now what we just saw, that if the only matter field that you have got is a scalar field, there's only one component, therefore there are only 3 degrees of freedom. So indeed it is true that by gauge choice, we can just eliminate. So these are pure gauge, the vector modes. We still have 4, and we'll talk about, therefore there's still some gauge freedom left over, because we should only have 3, and we got 2 scalar and 1 tensor. So the statement is that for gravitational waves, if you like, these are primordial gravitational waves. As I told you last time, the big difference is that the primordial gravitational waves, there is no source for them. The gravitational waves we saw before, which were emitted by stars and by black holes, they are all retarded solutions to some wave equation with some sources. Whereas here, these waves have just been there. Right? They are just there, they propagate. So there are no source, these are source free. In this scenario that we got, there could not be a source. The only source is scalar field, and the scalar field is not a tensor field, so it cannot really source the transverse traceless modes. You need here transverse traceless tensor field in order to source the transverse traceless modes. So these are source-free solutions to linearized Einstein's equations of our background solution. We have some background solution here, which is given by GAB and phi up here, that is fixed, and we are doing perturbations around that background solution, and then the gravitational waves just are source-free solutions on that background, and these are the 2 transverse traceless modes. And there are 2 of them. That is what they do. So when we talk about primordial gravitational waves, we are talking about this part of the gravitational perturbation. These are the primordial gravitational waves. So again, I told you the distinction. First is we do not have asymptotic flatness. So this is a question that you were asking before to me, that what is the difference between what we did in the second part and what people do in cosmology. So in cosmology, the statement is that there is no asymptotic flatness, so you don't go to a radiation zone to extract out the 2 degrees of freedom. You really have to do it everywhere. Second difference is that in this context, we really work in some approximation, linearized or second order linearized approximation. We don't know what we should mean by gravitational waves in full general relativity. This is important. I mean, this is surprising, but it's true. That in the cosmological context, we don't have a good notion of how to single out the 2 degrees of freedom in a gauge invariant manner in the full nonlinear theory. But in the linearized case, there is no problem. We can extract them, and these are the 2 modes of it. And finally, we also need to know, so these are 2, and these are given by this tensor modes. So this is T1 and T2, so I'll just call this as T1 of K. I stopped writing eta everywhere here. I should really write eta. Everything is a function of eta. So at the moment, everything is a function of eta, so it's easier for me just to remove this and say that for each eta, I got an expansion of this kind. Right? Instead of writing eta, because it's already a complicated equation, if I write eta here, it will be too muddy. So these 2 modes are tk, but here I can write tk of eta and t2 k of eta. So these are the 2 tensor modes. Yeah.
How can I be sure that the gauge transformations will always kill the vector modes? How there's an easy way of seeing that?
Yes, I mean in the sense of that. So the gauge transformations can kill this vector, will kill these vector modes, just because if like we just have two degrees of freedom are just in the gravitational field and in the scalar field. You're saying technically how this happened, is that the
Yeah, I
question?
mean, there are 3 degrees of freedom. I've done a decomposition. I don't see how, given the decomposition.
But because we haven't done, right? We really have to write down these equations and see that I can, with the source, I can actually do it. That is a detailed calculation. It's not something that I can just,
Okay. And
already.
we always keep the vector part.
Yeah, I mean, this is not totally trivial. Some reputable people in our community in loop quantum gravity have written papers about the behavior of vector boards in inflation and what is the effect of them on by loop corrections. And it's an empty paper, right? Because there are no vector modes in the gauge invariant vector modes in the case. So it's not trivial, right? I mean, in the sense these are people who know cosmology who have written such papers. So I don't want to say that it's trivial, but it's true. I mean, I think this because we only have 4 lectures left over, I had to go through very quickly.
And another question related to this. In case for some reason I want to use not theta but the other time, how this decomposition changes? Is it just replacing?
No, there's nothing changes here. Right? It's the same. It's just that here there will be a function of t up here,
Yeah.
and therefore the equations will. We can write down the equation. These satisfy with respect to t or with respect to eta. Doesn't make any difference. It's just that the equations are. Cosmologists have used eta because the equations become more transparent. I mean, of course, transparency is.
In doing the Fourier transform.
No, it's a spatial Fourier transform, right?
The spatial Fourier transform.
It's just a Fourier, so it doesn't care about time. I mean, I got the same. T equal to constant slice and eta equal to constant slices are the same.
Yeah, but the x component are different. The spatial part. Because one has a times x.
Oh, you're talking about if I had not pulled out this x.
Yeah.
No. So the statement is that then, I mean, okay. So your question is the following: supposing I did the Fourier transform not with respect to dx squared, but a squared eta times dx squared.
Yeah. So.
Then on each slice you have to do a different Fourier transform,
Yeah.
right? Because the metric is just expanding. X is changing. So x is expanding, and therefore k has to be shrinking. I mean, with respect to what we're doing up here. So you can do that, and so that you can just multiply this by a, and this by divide by a, and this will be the physical a. This in fact is a physical co-moving. K was a co-moving wave number, and k by a is going to be the physical moment. But then you have to say take care every time as to which k you are talking about. So this will also be k upon a. At what time this k is. The simplification here is that k is fixed once and for all, and therefore this co-moving k is fixed once and for all. So when you talk about, for example, I can compare k, I can say that more the so and so co-moving k at the onset of inflation is now entering the horizon today or something. We can talk about that. Otherwise, I will have to always convert into physical, distances up here. It's a matter of just simplicity in expressing what is happening up here. It has no deep content.
So, but if I only see the equation, that I will have some equation for.
There will be more derivatives, and the form will be very different. Yeah, I mean not very different, but the form will be different. Yeah, and it is confusing.
There's a way of converting it. It's not just replacing it.
No, you have to do it. No, it's not just replacing. Yeah, but once you have done it in this way, if you want to get what happens to the physical mode, you just divide and multiply. But if you want to, that's enough. But if you want to do something like the detailed equation, what is being satisfied, there will be different equations, precisely because one will have k and the other will have k upon a, which is time dependent, and so on and so forth. I mean, physically it is more satisfactory to do what you want to do, which is a of eta times dx. But the equations do become very complicated. I felt strongly that one should do the way you are saying is a of eta times dx. But then there are just unnecessary extra terms which don't add any physics anywhere. So that's why the cosmology is being smart. I've been just using the co-moving case up here. Okay. So these are the two tensor balls up here. And then one would like to know what are the equations that these two tensor balls satisfy. So the equations, dynamical equations, that the tensor mode satisfy is just block of the tensor. Now I'm going to put an index I up here, that I just goes 1 and 2 of x and eta, which is the same as 1 upon square root of g. Please note this because this is also one of the homework problems. 1 upon g times TAB, GAB. So the block with respect to any metric operating on functions is just 1 upon square root of g times GAB times dA times square root of g. So this is a determinant. This is not the most elegant way to write it, but this is the most economical way to calculate the box operator. This operating on Ti. So maybe I should call it T tilde here, because I call in the momentum space I did not have tilde, so I'll put in the position space tilde up here. So this is equal to 0. So this is the differential dynamical equation it satisfies. And when you expand this out, you just get T double prime K plus 2A prime upon A times T prime of K. Now I'm just dropping even I because the equation is the same for I equal to 1 and 2, so there is no reason you're keeping I. Let me just finish this line and then take the question. Plus K squared Ti. So here, this is the equation of physical space-time, but then the Fourier transform. So you can write down the equation of physical space-time, and write it on this T of x, and then check that if I do the Fourier transform, I just get this equation up here, where double prime still refers to eta, so it doesn't matter whether you are in the physical space or in the momentum space up here. And K, however, is the coefficient that I got here in the Fourier transform of Ti. So this is just the Fourier transform. Yeah.
Your expanded expression for the box operator still has a floating B index. So I think there's like a second derivative operator right there.
Yes, that's dB. Right. Thank you. So square root of G times dB.
This equation depends on the gauge we use to kill the bees?
This equation or this equation? This equation in general, this is just a box on, this is just nothing to do with cosmology really. Box on a function, it just always can be expanded out like that. So that's the first statement. In any coordinate system, of course, this is a coordinate system dependent, this is a general statement. In any coordinate system, we can do that. But now I expand this out, and I will get some equation, and the statement is that this is something that is really talking, where this, here we're not going back here. If you like, we did all these things to conclude that the equation of motion should be equal to this. Okay, and then I'm just simplifying this. So the statement is that in going from here to here, there's no assumption. In going from here to here, it's just a Fourier transform T. There's nothing. So the statement here is that, 1 second. So the statement up here is T tilde I, let me say T tilde x and eta is equal to the same thing that we wrote down there before, T naught squared K times . So that's the definition of all I need is a relation between this and this. The relation is just this. Right? It's just a Fourier transform on that. So the non-trivial things about this gauge and gauge fixing and etc. That all happened before we got this equation. Actually, for the tensor modes, you don't have tensor modes are gauge invariant by themselves, and therefore this gauge fixing. There's a second point that I'm making. It's not obvious, but it's true. The tensor modes are gauge invariant by themselves, and therefore this gauge fixing, which we eliminate some this mode and so on, it really doesn't affect the tensor modes. It does affect the scalar modes, as we'll see in a minute, but not tensor modes. You have a question?
Just in the box operators, you're not going to raise with the unperturbed metric, you're going to raise with the perturbed metric?
Oh, sorry. So this is the unperturbed metric, so good. So this is, I'm using in two different, this GAD is what I'm talking about always. So this is, I did call it something else at one stage,
You put a little zero on top or something.
No, I did not. See, this was supposed to be the Minkowski space. That's what that was a 0.
You had the B.
So when I don't, there is no lambda, then it is, okay. So,
There was a
so,
B.
so.
GAP, capital B.
Yeah, so this GAB. We should change the GAB to, let's just change it. This is the bold-faced GAB, just like this is bold-faced.
Oh, okay.
And then the statement is that the, right. Yeah, I said with a B, right? Yeah, it's a background. So this was the thing with the background. So let me now, sorry about this. So this is what I call background, and that is what I am using there. But I think it is better just to remove this B, and this is the background matrix. So thank you for all these questions. So the statement is that this equation up here is, of course, this refers to the background metric, and all these things refer to the background metric. So this perturbation is propagating on this background metric. It's not the full metric because we're only looking at linearized equations. So, okay. So these are the tensor-mores, and this is the equation that they satisfy. Now just one more thing that I would like to say. People also do another simplification which is important. Because in all these things, I'm not proving important things, which perhaps in a class one should do, but then the whole semester would have to be cosmology, which we, by your input, we decided not to do that. We just have one part in cosmology up here. So there are many simplifications that happen. So the thing that you just have to keep in mind at the moment is just that we have a background metric, which is Friedman, Lemaitre, Robertson, Walker, with a background scalar field, and they satisfy these equations. On that, we are perturbing. And I'm not doing the beautiful and nice and somewhat complicated theory of cosmological perturbations here. I'm just telling you the result. And the result is, that's what you have to keep in mind, that in fact, if the only matter field is a scalar field, then in the gauge invariant information is going to be put in the two transverse plane-space mode, which represent gravitational waves, and they satisfy some equation. It's just a block is what you sort of saw the equation would be for gravitational waves, and that is what is happening up here. So it's kind of motivated, but it's not derived by any means. And now we still have a scalar mode that we're going to talk about, because in all there are 3 degrees of freedom. There's a scalar mode. At the moment, we have got 2 scalar modes, S1 and S2 in geometry, and we also have the inflaton itself, the perturbation of this phi up here. We've got 3, but out of them, the statement is that the gauge will kill 2, and the gauge invariant, there's only going to be 1 gauge invariant combination. And we're going to discuss this in just 1 minute. But at the moment, what I would like to say is that is the following remark up here. That often it is interesting to just, the physical perturbation is this T, tensor perturbation. But often it is interesting to introduce a new variable, which is called chi. And this just define to be equal to, again, A of eta times dk of eta. And this definition, if you like, is suggested just by the form of this equation. There is no geometrical meaning to it. It's not like, previously I pulled out a scale factor and so on. It's not like that. I'm just looking at this equation and simplifying the equation. If I just do this, then I leave this as an exercise for you to check. It's a 2-line calculation. That chi will satisfy chi double prime k of eta plus a squared times k squared upon a squared minus a double prime, a triple prime, sorry, no, a double prime upon a cube times chi k. So it's not a very profound thing. What we've done is we wanted to eliminate a term which is a first derivative of the perturbation, first time derivative of perturbation. And we can eliminate it by just redefining the variable there, and then we get an equation which looks almost like the Schrodinger equation, right? It looks like second derivative here of with respect to eta, not Schrodinger time dependent equation. It's kind of mathematically it looks like a potential scattering equation. Somehow I got the wave function second derivative of the wave function plus some potential up here times the wave function is equal to 0. This is the equation that you would mathematically solve if you are doing time-independent Schrodinger equation. This is only a mathematical analogy, don't confuse it with anything real, but still you can draw intuition about the solutions of this equation because what you know about solutions to the standard Schrodinger equation in the time-independent case. Okay. So the important thing, as I said there, the only important thing is really that we have gotten rid of this term t prime. And now we just have a second time derivative, some things which depend on the background and on k and chi k. And this equation tells us what the behavior of solutions of the perturbations will be. Okay, what we have is really a background space-time with a background inflaton on it, and we're looking at the gravitational waves, the perturbations propagating on it. And we want to understand sort of physically what could happen. We would like to, what can happen is all in this equation, right? I mean, it's not anything new. I mean, we just have to draw it. And this is just a mathematical trick to actually simplify the equation to extract, so that the form is sufficiently simple that we can directly extract physics from it. So the first remark is that this quantity up here is precisely the scalar curvature divided by 6. Scalar curvature divided by scale. This scalar curvature is the 4D scalar curvature of the background. This is a 4D scalar curvature of the background. So what it is saying is that this term that I got extra term up here is a computation between k squared upon a squared times this. Now, as in answer to the question that Emmanuel asked, I already told you that the physical metric has a squared factor to it. Therefore, in this Fourier transform, if I have done it with respect to physical metric, the physical distance will be a times x, and therefore the physical wave number will be k upon a. So this is really the case. This is just the gravitational redshift, if you like. Namely, k physical is just equal to k upon a. This is co-moving. This is the mathematical one, and this a. I mean, this is what you would expect, right? As the universe expands, the physical wavelengths would be stretched by this scale factor, right? So because the physical length is being stretched. Okay? So physical wavelength is going to be stretched. So the physical wavelength is going to be a multiplied by the fiducial or the co-moving wavelength. The wave number is 1 upon physical wavelength, and therefore wave number is going to be shrunk by a factor k up here. So this equation can be rewritten as just chi double prime of k of eta plus a square times k physical square minus scalar curvature by 6. Now, one other thing that you notice immediately about this equation is that the equation doesn't care about the vector k. If I have vector k in the x direction with the magnitude k, or in the y direction with the magnitude k, the equation is same. So in fact, the solutions to this, I can easily omit, if I wanted, the vector k here. I can keep it, but it doesn't really add anything. I can keep it or I can leave it out. So sometimes I might keep it, sometimes I might leave it out. But the vector index up here doesn't have very much significance. It's only the magnitude of the vector that matters. Now here, so this equation, if this were constant, right, then it would look like chi double prime plus some constant is equal to 0. So the solutions are going to be exponential depending on the sign of this term up here. They're going to be either damped or they're going to be oscillatory, like the harmonic oscillator solutions. So when is the change going to come between the two? Well, there's a competition between the physical wave number and the scalar curvature. If in fact we are in a regime in which k physical is much larger than the scalar curvature, that means that the wavelength lambda physical is much less than the radius of curvature. K squared is much smaller than radius. So radius, this is like taking the square root if you like, because here I'm talking about K squared. So if I talk about K, then I will take square root up here. And if I invert that, I will just get the radius of curvature. I'm not worrying about the factor of 6 up here. So if the wave number is very large or the wavelength is very small, then this term just behaves. Then the equation reduces to chi double prime k of eta plus a squared times square times 5k equal to 0. But we just saw that k physical is k by a, therefore I can just remove this, and this is just equal to k squared chi k. So now the equation just looks like the harmonic oscillator equation, or if you like, the mode is behaving, is evolving in time as though it was in Minkowski space. Because all reference to the curvature is gone. The reference to the curvature was here, or the scale factor changing reference was here up here. All of those things are gone. And I'm just left with chi double prime of k of eta plus k squared times chi k of eta is equal to 0. So this is really the mode evolves as though in Minkowski space. So the statement is that if the wavelength is very large, if the wavelength is very small, and the radius of compared to the radius of curvature, then the wavelength, the propagation of this mode doesn't really see the radius of curvature. It doesn't see that the space is curved on this length scale, because it is just feeling this little thing where the curvature is not changing at all. So it propagates as though it is in flat space. It's a little bit confusing at the first. The statement is that the highest energy, the smallest wavelength modes, propagate as though they are in flat space. They don't see the curvature at all. It is only in the opposite case that they see curvature. So in the opposite case, the opposite case will be when K physical is much less than r by 6. And then the equation just becomes chi double prime k minus a squared. But we just saw here that this was just this equation up here, a squared times that will be just equal to a double prime upon a times chi k. I'm just going back to the original form. I could have left it in terms of scalar curvature times k is equal to 0. Again, I did that in part because I just wanted to write everything in terms of k now, and not in terms of k physical or anything like that. So we just have the equation for each co-moving mode. It looks like that, and then therefore obviously, if in fact a double prime over a is positive, then what you're going to find is that so a double prime over a is positive. You have to go back to Raychaudhuri equation and see what phase you're talking about. Then this is going to be exponentially damped. So then it's going to be exponentially damped or growth. So the two modes behave very differently. The short wavelength modes, they are merely going around as though it is in Minkowski space. The long wavelength modes see the curvature, and they're either damped exponentially or they're enhanced exponentially, one or the other. That is going to happen. And this is kind of the key point. It just seems very simple, but it's a key point about what happens during inflation. At the beginning of the inflation, the modes of interest have physical wavelength which is very small, okay, compared to the radius of curvature. And therefore they are propagating as though they are in Minkowski space. But once their wavelength, but their wavelength, physical wavelength, is actually growing very rapidly with the scale factor. So therefore, there's a competition between the curvature and the scale factor. If the wavelength becomes larger than the radius of curvature, then suddenly we enter into this regime and the behavior changes qualitatively. And this is what we're going to come back to several times. Okay, so these are the basic things about tensor modes. I do realize that this is rather fast, but I also have felt, since I started teaching these advanced courses many years ago, that if in an advanced course you understand everything, then the course is not so good. I mean, the whole point here is that you should be able to revisit your notes for 2 years, 3 years, 5 years. Sometimes I revisit my notes even today, like so many years ago after that, just to see what was said. And you might actually learn new things in that. So please keep your notes and revisit them. It is not my expectation throughout the course. I made it clear in the very beginning, but let me make it clear also. It's not my expectation that you understand everything in this course. But the whole point is that you get a good, solid global picture, not just qualitative one, but really how this step is done, then this step is done, then this step is done, so that you can fill in the gaps now and in the future as time goes on. The last thing that I just wanted to tell you was about the scalar modes. So what we do is, we got these three things. We got S1 of k, S2 of k. These are the geometric scalar modes, and we got phi. This is the matter field. And I just written down here equation under gauge behavior. Under gauge, all these three things change. However, there's a combination of them which is gauge invariant. It's not and that combination is the following. It is the it is qk. I'll not write eta, it is of course at each eta. Qk is equal to 5k minus 8 dot. These are dots, not primes, but we can convert it into primes very easily. This is gauge invariant. This combination is gauge invariant. I'm just stating it. I'm not proving it. It was first obtained independently by Mukhanov and Sasaki. So it is often called the Mukhanov-Sasaki gauge invariant variable. That's what it is. But the way that they found it was quite elaborate. I mean, it was long calculations, and the structure was not clear. It's a fact, but the structure was not clear. And a very nice Hamiltonian treatment was given by Langlois. And this is a paper in Classical Quantum Gravity, 11, page 389, 1994. See, those of you who know about constraint systems, if you go to the Hamiltonian framework, then it is quite easy, or it's much easier to understand how to form the gauge invariant observables. There are sort of systematic procedure to find it, and that's what Langlois did. And he found that in addition to the tensor modes, which are of course gauge invariant almost by inspection, short calculation, there is also a scalar mode which is gauge invariant, and only one. And in fact, from Hamiltonian perspective, we have these Dirac observables. So to begin with, I got some phase space. There are some constraints. You can do it mode by mode. So it's really a finite dimensional system, because for each k, you just have T1 and T2 are just two variables, right? For each k. So you just have a finite number of variables up here, and therefore you can do a finite dimensional Hamiltonian reduction, and you find what the gauging invariant variables are. This is a systematic procedure. The catch is that this paper, unfortunately, has many typos. And of course, that's unfortunate because this is all, the key thing is how do we arrive here up here. But one of our former postdocs, William Nelson, has actually corrected all the typos, and I got the corrected version, which I'll put today on the web. So corrected version is due to Nelson. I happened to meet Langwa in a conference in September, so just last year, and I told him that, this paper is so beautiful but has so many typos, unfortunately. He said, yeah, I know, I wanted to go back and correct it, but so many years ago, it was very difficult to sort of correct it or something. But William had sent him, and so he was very appreciative of the fact that William had gone to the trouble to correct everything. So I'll put this in there. So this is called the Mukherjee variable. So we got one scalar mode, and we got two tensor modes. And the final thing is, what equation does this mode satisfy? And not very surprisingly now, you again get the block operator with respect to a background metric. So all with respect to the background metric, G or GB, whichever you want to call it, of Q of X and eta. Again, QK would be the Fourier transform of X and eta. So exactly like this framework, namely Q of X and eta will be equal to 1 upon V naught times square root times K, sum over K times Q of eta C to the RK dot X. By the way, though, if you want to go to the continuum, you probably know all these things, but let me just remind you, you just replace everywhere you see this, you just replace it by d3k upon 2 pi q. So that is the replacement that you do in order to do the continuum. And this is the convention that is used in the cosmology literature. They always, in the Fourier transform, they put the 2 pi cube factor in the d3k integral, and therefore in the d3x integral, there is no factor of 2 pi at all. In field theory, particle physics kind of field theory book, I think typically they have 2 pi raised to 3 by 2 and 2 pi raised to 3 by 2. They are divided equally between the two, between the x representation and the k representation. But in cosmology literature, the factor is put just here. So we get this, but then there is a potential up here. So there's a potential which depends. So this potential is determined by background quantities, of course. So it does depends only on eta. So here the tensor equation was just source-free wave equation. Here it is not a source-free wave equation, but it is a wave equation with respect to. So just like here, here is the wave equation with respect to the background, just like there, plus a certain potential term. But it turns out that when you put the numbers in, that during inflation, this term is completely negligible. So this is something that one has to check, case by case for the potentials and so on. So this U will depend on background quantities, and those background quantities will depend on the potential V that we have got for the scalar field. But this is negligible, therefore, in practice, during inflation, you can just look at the wave equation for the scalar mode and the wave equation for the two tensor modes. And again, since these are transverse traceless, what we have done is we have taken out the polarization tensor, which is in this UU minus VV. These are the two polarization tensors that are often called epsilon mu nu in the particle physics or cosmology literature. So these are the two polarization tensors that we got, and these are the components along those polarization tensors. And then the statement is that those components just satisfy the wave equation, and So I got these two of them, and I got one scalar field. And this is what we use in cosmology. I'm sorry, much later than I thought. I usually have alarm, I forgot to set it today. Let us stop, and let's continue on Wednesday, and we'll do quantum field theory begin with quantum field theory on Wednesday. And then the last two lectures will be applying this perturbation plus quantum field theory and get observational consequences.